Okay, so last time we stopped this one, let's throw in some slides that might make this a little more clearer. Properties of complex numbers. So I want to get into the complex notation of a wave because that will be important for phasing purposes. And to do that, we'll start off with just some wave basics. And I apologize if this is a fairly simple level start to it. But I don't know how many of you have a physics background, how many of you have a biology background, or a chemistry background. But a wave is very simply described as a motion that's repeated exactly at regular time intervals. It has a wavelength, one period. That's the time it's actually repeated. And it has an amplitude. And the number of oscillations in 1 second is called the frequency. Frequency is measured in hertz. And the velocity is given by frequency times the wave. This should be about that. So V is velocity, F is frequency, and lambda is the wavelength. So wave, very simple concept. Basically, it's a repeating motion over time or space. The simplest form of wave is a sinusoidal wave. Sine wave has a maximum positive amplitude at 90 degrees and a minimum at 270. A cosine wave is very similar to a sine wave, but if you plot a cosine wave, so if you have a sine wave has maximum at 90 degrees, so sine wave is like that. A cosine wave just has a maximum there. So a cosine wave has a maximum of 0 degrees. A sine wave has a maximum of 90 degrees. And that's just the difference between the cosine and sine wave. A wave has amplitude and wavelength, and it carries energy. The energy it carries is this oscillation here. The rate of energy transfer is the intensity. So in reflection, this energy, when it hits your CCD or your phosphor or your film or whatever you're detecting it, that's the energy in the wave, that's the intensity of the reflection. The intensity is proportional to the square of the amplitude. In crystallography, we use radians for the angles, but I'll come back to that in a second. Pi radians is equal to 180 degrees. And cosines are normally used for most crystallographic purposes. Now, this is a soap bubble. Does anyone know why a soap bubble has multiple colors? It's basically because of light waves interacting. And it's a process called interference. An interference is the supposition of two or more waves that result in a new wave pattern. This is the principle of interference, and I'll show you it graphically in a second. But it basically says that a superposition of waves, the resultant displacement at a point is equal to the sum of displacements of different waves at that point. So if a crest meets a crest, then you double the displacement. If a crest meets a trough, then you have 0 displacement. And if a trough meets a trough, then you have double the displacement. Phase is something that describes where you are on this wave. So if I have this wave coming in here, we'll use the cosine wave, because we're going to be talking mostly about cosine. I can say the phase, if the wave is 90 degrees, or 180 degrees, or 270 degrees, or 360 degrees. The phase just describes where you are on the wave. And phase will become important because this is the information we actually use in crystallography. Now, when the waves are in phase, that means they interfere constructively. So if I have another wave that's down here, which has the same frequency as that wave there, if I have those together, and we'll say that's 1 and 0, what I get is another wave out where the amplitude is 2. And I'll show you that graphically in a second. And when they have the same phase, when you add them together, they interfere constructively. If they have opposite phase, they interfere destructively. And in simple terms, you can add or subtract waves, but you have to account for the phase. Another way of looking at phase is to think of the moon. If you've got the moon here, it's a new moon. And as you go around this circle here, it goes into partial moons like that. And this is going to lead into the Argand diagram a little bit, because the Argand diagram actually explains phase. The moon is still there, but the amount of light that you get changes as you go around here, or the amplitude changes as you go around here. I mentioned this on the diagram before. Phase specifies where the peak of wave is compared to its origin. So this is the cosine wave here, it has a peak of 0. This is in the top there is the phase in radians, and pi over 2 is equal to 90 radians, pi is equal to 180 radians, 3 pi over 2 is 270 radians, and 2 pi is 360 radians. And pi comes in useful because it makes the mathematical notation very easily later on. Now, in this particular case here, I've got 3 different waves that we've got. This black wave, the red wave, the blue wave. Now what we've done is we've changed the phase of the red wave by pi over 2 radians. And when you change the phase of the red wave by pi over 2 radians, you move it across here. Now, if we change the phase by pi radians, you get the blue wave. So we've got pi over 2 radians, and it's shifted it by 90 degrees. Pi radians, and it shifted it by 180 degrees. So we've essentially moved the position of the wave along. Now, been on an aircraft before, or in a car or something, with worn headphones that are noise cancelling? Okay, they reduce the background noise if you wear it. But essentially what it does is you have a noise that's in red. It's from the background environment. And what these headphones do is they record that noise and they invert it. And they play the inverted noise into the ear. And when you add these two together, you get 0. So a positive plus a negative is 0. Negative plus a positive is 0. So that's how noise cancelling headphones work. And that's a process called destructive interference. And this is a mathematical example of it. If you have 2 waves that are pi out of phase, the first one has a peak at 1, the second one has a peak at -1, at 0 radians. And if you follow these waves along and you add them together, what you get out is nothing. These 2 waves interfere and you get nothing that's actually produced. Now, anyone been to a concert, rock concert? Must have been to a decent concert. This was my background before getting into crystallography. I actually did roadie work. And what we do at a concert is, when you play music, if you're in the front of the concert and you play, the person who's at the front sees you play something, and hears the noise that's associated with that. In a big venue, the person at the back sees you go like that, and then about a half second later, here's the noise. So what you do is you set up speakers at the front, but you also set up speakers at the back. And that way they get the noise instantaneously with the actual playing. Well, this gets into a process of constructive interference, which is, with a rock band is what we want. It makes things far more noisy. But in this case, the waves are in phase. So you have these 2 waves here that have the same amplitude. They don't necessarily have the same amplitude, but they have to have the same frequency and the same phase. When you put a peak and a peak, the resultant wave adds. When you've got a 0 and a 0, you get nothing. When you get a trough and a trough, you get that added together. So in this particular case, with constructive interference, you get the doubling of the actual size of the wave. Now this occurs on many length scales. I've talked about sound. It also occurs in geographical length scales. This is Gibraltar in Spain, this is Morocco down here. And you can see that you've got this wave that's coming in here, which I believe is a tidal wave. And then you have these lines where you have that line out there, this line out there, that line out there. They're all constructive interference effects. And this is very similar to crystallography. We have a wave coming into a crystal, we've got molecules that are sitting in that crystal, there's a gap between them, and you get these lines of constructive interference that are coming out, which are the reflections. Now, I went into this last time. I'm going to go over this, skip over this very quickly, but just to say that X-rays are part of the electromagnetic spectrum. And if you look at the electromagnetic spectrum and look where visible light is about 1 micron, 10 to the minus 6 meters. You can express that in terms of energy. It's about 1 eV, and that's about the size of E. coli or cells. Viruses are smaller, proteins are even smaller, and atoms are even smaller. And because we are below the size of visible light when we're looking at things, we can't use a microscope to look at structure. So we use X-rays, which are up there. They're about the same wavelength size as atoms or the bonds in atoms. And then we use X-ray diffraction. Now, I showed you this last time. The wavelength of that L should be a lambda, but the wavelength is proportional to the speed of light divided by the frequency. And the photon energy is given by Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. Because when you go to the synchrotron, or when you go to an X-ray free electron laser source or large experimental facilities, in the crystallographic lab you express wavelength in terms of angstrom or even nanometers if you're more of a physicist. When you go to the high-energy X-ray sources, instead of expressing the wavelength in angstrom, they actually express what the machine produces in terms of energy. And that's how you convert between the two. That's equation there. So let's revisit the cosine wave here. So a pure cosine wave can be expressed with W being the quantity the wave disturbs, so whether that is sound, whether it's water, whether it's electrons in the atom, can be expressed by the amplitude, a function of the direction of propagation, the speed of light, the time, the wavelength, and the phase. And that P is phase there, which I'll come out very well. And for unit amplitude and wavelength, so if we consider a wavelength of 1 and an amplitude of 1, we can express this very simply as W is equal to cosine of the phase at position. I've showed you that one. Now I'm going to show you what complex number, or how complex numbers can be involved. All problems are complex. They have real and imaginary components. It's a geek joke. But this is what's called an Argand diagram. And what it does is it expresses a complex number as a real component, the x-axis, and as an imaginary component, the y-axis. And if we imagine our wave here, this wave has unit amplitude. So at this point here, if we had an Argand diagram, so if we had our Argand diagram for this point here, it has unit amplitude, that's the amplitude here, but it has 0 phase. So our Argand diagram would be a line that looks like that. If we were to take this position here and do the Argand diagram for that, in this position, it has 90 degrees phase, but it still has the same amplitude. It's got the same energy, so it is here, 90 degrees phase. We take the Argand diagram down there, it looks like that. So the Argand diagram is a way of representing any point in this wave in two-dimensional space, which captures the energy of the wave but also the phase of it. Now this is important because if you remember the equation before, where we had a cosine function, not a sine function here, we can actually express the complex number as in this notation, where it has a real value times this imaginary number with phase there, or a real value of x plus an imaginary component y, and this can be expressed in terms of a cosine function. And if I go onto that diagram there, and we take the wave, we have a wave taken at point 0, the Argand diagram looks like that. Pi over 2, it looks like that. Pi over 4, it looks like that. Pi over 5 pi over 4, just as an example, it looks like that. Now, can you see, if I propagate that diagram down, the position in this orientation, in real space, wherever it is actually very nicely defining the amplitude at any point. So in this one here, where we're at 0 degrees, the Argand diagram looks like that. And if I propagate that down, the intensity at that point is at the 0 position. Now if I move in phase to that point and I propagate it down, the intensity is there. If I move here, the intensity is there. So the Argand diagram is describing both the phase of the wave and the amplitude at the point where I sample that wave. If we go to the example of destructive interference, that's the plot I showed you before where we had two waves, and then when we add them together, because the peak in one is equal to the negative peak in the other, they equal 0. If I take the Argand diagram of those two waves, I have this wave here with a certain amplitude given by this axis, and a certain phase given by this angle. And I have this wave here, which is completely out of phase, it's in the opposite direction. And if I add these two together, what I get is nothing. Destructive interference, no wave. So those two added together give no wave at all. So if you think of this in terms of the concepts of X-ray diffraction, this is the case where you've got gaps between your reflections, where you've got nothing there. This is because you get destructive interference and nothing occurs. If you take the opposite case, where you've got waves that are in phase, wave 1 looks like this, wave 2 looks like this. And the way the Argand diagram works is you can add these two together just by extending that onto the end there, because it's going in the same direction. And this is what the wave looks like. And now you have a wave that has the same phase, and it has double the amplitude. It has the amplitude of wave 1 plus wave 2. And that's constructive interference shown in the Argand diagram format. Why is this important to diffraction? Well, this is Huygens' principle. Waves spread out as they pass through slits. So if you imagine a wave coming through here, there's a slit, these waves that are formed, the peaks are in red, the troughs are in blue, so it's low, high, low, high, low, high, low, high. And if you have a second set of slits here, you get the same propagation of these waves, and every time you get a peak, you get constructive interference. Every time you get a peak and a trough, in these cases here, you get destructive interference. So if you were to look at the light that's coming from this, you'd see a bright light here, you'd see no light here, you'd see a bright light here, no light there, and a bright light there. And that's the process of diffraction. That's a diffraction property. Now this is a really important diagram. And the reason it's really important is what I showed you before about constructive interference. So when you have two waves that are in phase, the resultant one is a wave that's twice as big. Okay, so if I move this, if I shift the phase of this so that the peak is now at the trough of that, what happens?
Can you say that again, please?
So if I shift this wave so that now it looks like that, what is my sum?
Zero.
Zero, okay. And what have I done to this wave?
Shifted the phase.
I've shifted the phase, or I've moved the wave. And how much have I moved it by?
Pi over 2.
Pi over 2. And pi over 2 is how many wavelengths?
Quarter.
It's actually half a wavelength.
Half a wavelength.
So what I've done is I've shifted the wave by about half a wavelength, and I've made the reflection disappear. I've made destructive interference occur. So if I wanted to shift the wave further to make the interference come back, constructive interference come back, how much would I move this wave by? Pi. Or one wavelength. So if I've got two identical waves, because it's a periodic function, and I move that by one wavelength, it's the same function that causes constructive interference. Now what we can say is we can calculate geometrically what the distance is from this point to any arbitrary point on a detector, and this point to any arbitrary point on a detector. And what we can say is if the difference in those two distances is a whole wavelength, then we would see constructive interference at that point. Okay? So this is a very simple geometric calculation. You've got one distance, R1, you've got one distance, R2, and for a certain angle, R1 will be exactly one wavelength longer than R2. And if you do the geometry, your condition is that R1 minus R2 is equal to lambda, one whole wavelength. And your simple geometry will tell you that that lambda is equal to d sine theta, where d is the distance between those two gaps in that little grating that we have, those two holes there. And this gives you an equation where n is a whole number, so one wavelength, two wavelengths, three wavelengths, times the wavelength is equal to that d sine theta. Now that is Bragg's law. And this is how diffraction works. N lambda equals 2d sine theta. You know what there's a 2 in there? Bragg's law is a reflection. It's actually two distances there. You've got one distance which is d sine theta and one distance which is d sine theta. And that's where the factor of 2 comes in. N lambda equals 2d sine theta. And that is the condition for diffraction occurring in a crystal. Diffraction occurs where an integer times the wavelength is equal to 2d, and d is the d-spacing in the crystal, or d-spacing in the particular reflection, times the sine of the angle of the reflection. So the only time you get a reflection is when n lambda equals 2d sine theta. That's Bragg's law. Now, the sine function is related with the position of the reflection. So, we're going to be talking about waves and crystals. It's a nice picture of a wave. I usually give this particular part of the lecture later in the year when some of the snow is actually hit. But what we can think of a crystal as a cosine grating. Now, what do I mean by this? Now, this is actually from a book by Ed Lappin and Pat Lowell. And what I mean is when we think of a protein structure, we're not thinking of distinct atoms. The atoms themselves don't scatter X-rays. It's the electron cloud around. And what we have is an atom here, for example, that has most of the electrons are there and then it dissipates. Then an atom here where most of the electrons are there. And we have this grating of high electron density and low electron density. Now, for the moment, we'll just consider it as regular grating, so atom, atom, atom. And what happens is when a wave comes in, you get diffraction that occurs. And the diffraction is perpendicular to where this cosine wave was. I won't show you the maths on that, but that's what you get. And if you were to rotate this cosine grating, your diffraction rotates. If you rotate it further, it goes vertical. You notice that most of the beam goes straight through. It's only a small proportion that's actually diffracted out. It's exactly what I showed you before, where we had the points where you get constructive interference, because this cosine function is acting as a sort of a grating where you're allowed to pass through one part and not pass through the other part. So if you rotate the grating, you rotate the diffraction. Now in this one here, what I've done is I've changed the size of the grating. And you see for the fine grating, the diffracted waves are quite far apart. And for the coarse grating, they're quite close together. So this is just a mathematical function. It goes into the distance between the gratings there, which is the d-spacing. You'll find if you look at that equation, you do a small d-spacing, the angle becomes quite large. If you do a large d-spacing, the angle becomes quite small. And what that's telling you is that fine details are at greater angular extents in the diffraction pattern, and small details are at smaller angular extents in the diffraction pattern. So if you were to stretch the grating, the spots move closer together. If you compress it, they move further apart. Now, if you make the intensity of the grating stronger, the diffraction becomes stronger. So if you think of this as an electron density function, what this means is if you have high molecular weight atoms, they have a lot of electrons in, so they would make this cosine grating of the atoms higher. They'll give stronger reflections. So the higher the molecular weight, the stronger the reflection you get from it. Conversely, if they were lower molecular weight, the diffracted waves become weaker. And if you have no contrast, you have no diffraction. You have no density contrast. Now, if I take that grating and I say that my crystal has an array of atoms in these positions, and then it has an array of atoms in those positions, and an array of atoms in those positions, what you do is you start to add up this grating of this effect. And you go from an example where you have high, lower, lower, and lower. So you start to add up these order of these reflections. And this is what produces the diffraction pattern. It's a sampling of the space of finer and finer details. Now that's the visual idea of it. This is what it looks like in reality. And this is basically the explanation of what a diffraction grating looks like. I'll leave this for you for something for you to read. The contrast profile from a one-dimensional square-grained crystal can be written as the sum of cosines. Now this is important, that diffraction can be made up of the sum of all these different cosine gratings within that crystal. G0, G1, G2, G3. You can write it in an equation that looks like that. So what it's essentially saying is that arbitrary diffraction there is the sum of first order diffraction grating, the second order, the third order, so on and so forth. So it's the first order plus the second order is equal to the final thing. That one. Now, the gratings that I talk about have altitude. That's the contrast between them. So we have a grating in green here and a grating in red. In the red, you'll notice that the white is more intense and the black is more intense than the blue. So this would be different, a stronger diffracting atom, whereas the green one here would be a weaker diffracting atom. They can have different spatial frequencies, so you may have atoms that are closer together or further apart. And they can have different phase. That means the atoms would have positions in the crystal. So that cosine idea of expressing what a crystal looks like actually comes into different atoms, different positions within the molecule, different positions within the crystal.
Can you say that last part one more time?
Sure. So what I'm doing is taking a one-dimensional crystal. Let's see if I can illustrate it with a diagram I have. So there's a generic protein. Just realised I can't draw the same shape again. So what we're doing for this cosine grating is we're thinking of a one-dimensional slice across a crystal here. Okay? Now, say we've got an atom that sits there, an atom that sits there, and an atom that sits there. If I were to express the electron density as a function of some kind of curve, it would be that atom there, that atom there, that atom there. Now it's a crystal, so it repeats. And what I've done here is this is the actual electron density, where it's 0 here, and it's a maximum where that atom actually is. And we can sort of express that in the form of a cosine curve, where the peaks represent where the atom is, and the trough represents where it's absolutely not. In the real case, we ignore this trough here. And I'll get into how we can ignore that in a minute. Now, this has a certain intensity, which is due to the atom type. So if it's a selenium atom, this is quite intense. If it's a carbon atom, it's less intense. So that's what the amplitude is, amplitude contrast. Now, spatial frequency, we may have two of these atoms. Maybe another one that sits here and another one that sits there. And that means what we have is instead of this one wave that looks like that, we have another wave. Which looks like that. And what that means is it's got a higher frequency. And it's got a higher frequency simply because instead of the one, we've now got two. So that would be the higher frequency case. We have one in that case, and two in that case. And then the spatial phase is these molecules, or these proteins may be further apart. So, this one might not be present. In which case, what we get is a graph that has these two peaks here, a gap, and then two peaks there. And that's the spatial phase. So this is just an example of taking a one-dimensional slice for a crystal, which actually makes the mathematics a little easier to kind of understand, especially with one dimension. Does that make more sense? Okay. So each pair of reflections in a crystal's diffraction pattern can be accounted for by the diffraction from a single cosine protein. The entire diffraction pattern can be mimicked by the diffraction from the sum of many cosine proteins. And if the diffraction patterns of two objects are similar, then the objects themselves must be similar. And therefore, the sum of the cosine gradients must look like the crystal. What that effectively is saying is that if I start doing one cosine gradient through here, and another one slightly up there, and another one slightly up there, and I start to add all these together, at least in the one dimension, they'll look like a diffraction pattern in one dimension. If I take all 3 dimensions, what I'll get is a set of constructive interference points which will start to look like a diffraction pattern in 3-dimensional space. And the point about this is it can be explained as just a very simple summation of cosines. And this is going to get us into the Fourier series. This was Jean-Baptiste Fourier, born in 1763. And in 1807, he came up with an idea. He said that any periodic function could be rewritten as a weighted sum of sines and cosines of different frequencies. The mathematicians at the time thought that the idea was pure bullshit. didn't believe it. And it wasn't until 1878 where the idea was first published in English and it started to be used. To change a signal to a Fourier series, we perform a Fourier transform. To change the Fourier transform to a signal, we perform an inverse Fourier transform. I'll show you what that is in a second. Lord Kelvin had a very nice quote. That's Kelvin from the temperature measurement. He said that Fourier's theorem is not only one of the most beautiful results of modern analysis, but it may be said to furnish an indispensable instrument in the treatment of nearly every recondite question in modern physics. So Lord Kelvin thought this was pretty important. It is the very cornerstone of what we do in terms of diffraction, in terms of refining data, in terms of working with the structure. Lord Kelvin is famous for a number of other quotes. Heavier than air flying machines are impossible, radio has no future, and in science there is only physics. All the rest is stamp collecting. So, you know, 1 out of 3 is not bad. So what do I mean by Fourier series? Well, I've got the same kind of notation again here. What I've done is I've taken the unit cell with an arbitrary crystal that has this very strange formula of CCO. We have 2 carbons and an oxygen. Oxygen has more electrons in the outer shell than carbon, so the vertical axis here is the electron density. What we can do is look at that electron density there. We can say, supposing we had to wear glasses and we couldn't see properly, and we still had a fuzzy picture. And what you'd see is you've got the case where you've got these 2 carbons and this oxygen. And to a first approximation, what this looks like is something there and something there. Agreed? Okay? Now, that's a low-resolution picture of it. And that's basically a cosine wave that has a frequency of 2. Now, we look at that, and suppose we say, okay, I can see this with a bit more clarity now. And it looks like, so there's the cosine wave that looks like that. It actually looks like this bit here has a couple of things. I'll plot them like that. That one there has 1. And you see how this one is starting to add to that, and then these 2 are starting to add to that. And then finally, if we add a third cosine frequency, we start to see that, yeah, we've got something there, we've got something there. It turns out that this one here is actually negative. But if I add this to it, it becomes 0. And there's nothing there. It's right before the next oxygen. If I add this one to that one and that one, it all becomes positive. It starts to get to the peak of the oxygen. So what I've done is taken a cosine wave with a frequency of 3. I've added a third cosine wave with a frequency of 5. When I add all these together, I get this red wave here. Now, can you see that the red wave is very, very similar to the electron density that I plotted above? But you'll also notice it's not exactly correct. If you look here, it's got a little peak there. It's got a little peak there. And when you look at an electron density map, what you're doing is you're taking these frequency components, you're adding them back together, you're looking at the map here, and this is the noise in the map. Now, do you know what those frequency components relate to? We've got the HKLs we talked about in the last lecture. The higher the order of the HKLs, the higher the frequency component of these cosines that are added together. So as you get higher and higher and higher frequency, your reconstruction of that electron density becomes more and more accurate. Now, what the Fourier series does is it says that the unit cell can be represented by a summation of cosines. These are the cosines here. So 8 different cosines. The first cosine, frequency 1, has this amplitude. The second cosine, frequency 2, has that amplitude. Third, fourth, fifth, sixth. So that The Fourier transform is the frequency of information on the components of the waves that describe the real space. And it's the transform of the itself. And what we actually record as a diffraction pattern is the Fourier transform. If you have a lens in optics, everything that occurs before the lens is a Fourier transform of light. And what the lens does is an inverse Fourier transform, gives you the picture. What we're recording is, if we took the lens out, is the Fourier transform. That's what X-ray diffraction is. Now, if we represent the image in 3 dimensions, this is where the amplitude is represented by color saturation. So the more intense this color, the higher the amplitude. And then the phase is given by what color it is. So we have both amplitude and phase information here. And you can see that the Fourier transform of a duck looks like this. The Fourier transform of a cat looks like that. That's what a diffraction pattern looks like. Now in real space, if you take an atom and do a Fourier transform, you get this diffuse kind of circular structure. It really has amplitude information, really just a single phase because you've just got something that's in one position. If you take a molecule, it starts to look like this. And then if you take molecules that are in some kind of ordered lattice, you start to get a diffraction pattern. And you'll notice it's more intense in the center, it's less intense as it gets outside. This is the higher frequency information, this is higher orders of the Miller indices. That is more detailed information. This is the lower detailed information. So if I look at that with my fuzzy view, it's essentially the same as that red spot there. So the center stuff is low resolution, outside is higher resolution. So the diffraction pattern is a Fourier transform of the repeating unit making up the crystal. The macromolecule repeated within the crystal is an inverse Fourier transform of the diffraction pattern. So the diffraction pattern is a Fourier transform of what's in the crystal. And if you do the same Fourier transform, the inverse Fourier transform of the diffraction pattern, you should be able to get back to what the crystal looks like. And what we do is that inverse Fourier transform. But it's a little bit harder than just doing a very simple mathematical function because we lose some of the information, we lose the phase information. We lose the information in that pattern about what that hue is. If I go back to the pattern, when we record a diffraction pattern, it's monochromatic, it's black or white. And what we're recording is intensity. What we don't get is this color, which represents phase. We lose that information. That's one of the major problems in crystallography, the phase problem. Why do you think it's difficult to record phase?
So you don't have your incident beam is not all in the same phase.
That's one of the problems.
Is the frequency so high?
Yes. Yes. If you imagine the speed of light and how small that wavelength is, imagine what I've got to have as a detector if I wanted to record what that phase was. It's just a physical impossibility. If I could slow the light down, I won't go through even our function. This is just for a lot of stuff to do. But for a general function, ignore the URI, you can express the Fourier series as a summation of cosines and sines. And then the Fourier transform is taking that back to from phase space into real space. Again, I'm not going to go into the math behind that because you don't really need to know the exact details, you just need to know what occurs. But the important point is that any shape can be expressed as a a function of Fourier components. So in this particular case, we're plotting this function here. This has become garbled. My font is not correct on this for some reason. But what I'm showing you here is that a summation of sine curves, can actually make a square wave. So a summation of curves can actually make a square wave. And that's what it looks like. It's, that's the first one, first component, first term. That's the second term. So if you can see where the maximum is, and then I add the second term. The second term is actually got a trough where that maximum was, so that will lower the curvature of it. I can add a third term. I can add the fifth term, all the way up to the 10th term. And if I actually do the addition of those terms, you can see how I get to higher and higher frequency. I start to more accurately reproduce the square wave. What this is telling you is that the higher the frequency of the information, the higher the resolution, the higher the lower indices, the more accurate you reproduce the function that's actually representing what the true state of what you're looking at is, in this case, a square wave. This is what resolution is. The higher the frequency information, the more accurate the picture of what you're looking at. So that was a square wave, so I can use a set of curves to produce a very 90-degree edge through. I'm going to convince you that I can also do very, very sharp edges, a triangular wave, by going for a cosine function, number of successive terms. And we add all these terms up. You can see how I start to build sort of sawtooth function. Now, there's something that's important here as well. Can you see from that Fourier transform about the first term, the second term, the third term, and the fourth term? Notice how they're divided by 1, by 3, by 5, by 7. When you look at a diffraction pattern, it's fairly intense in the center. That's the low resolution term. And as the diffraction goes out, the intensity goes down. This is what we're seeing. This is why it's divided by 3, divided by 5, divided by 7, on average. That's why the information is becoming less intense as you go out, as you get higher and higher detail. So that's become garbled due to my font. But that A with a 0 over the top is actually a summation symbol. So the Fourier Transform, Fourier Series is a summation of 1 over the crystal lattice of these cosines and sines. So the font is garbled, unfortunately. So what does this mean? Well, it's pretty obvious, but basically, the low resolution first order terms give low resolution detail. As you add terms, you get higher and higher resolution. And then finally, you get the highest resolution. And before you ask, I know this is not HWI, I get to talk somewhere else. So I'm not that bad on geography. That's Canisius College. In real space, or in terms of the electron density map, the concept of resolution is given by this. For some reason, that slide back down was black and it's gone to white. But essentially what you're trying to do is to go from something which is a little bit ambiguous at about 3 angstrom there, that's number 1, down to about 2.5 to 2 to 1.5 to 1.25 with 1 angstrom. And the importance is that at low resolution, this happens to be insulin with the drug that's in there. And in the low resolution map, you saw 1 drug molecule bridging 2 insulin molecules. At high resolution, it turns out that 2 drug molecules are bridging 1 insulin molecule. So that's kind of important to know how the molecule is working. If you wanted to design something bigger that would go in there, but also to get an understanding of what might be a good dose for that particular case. In terms of pharmaceutical design, between 2.5 angstrom is the real cutoff. You probably want about 2.2 to be able to resolve what the different amino acids are at different positions. If you start recording data at 1 angstrom, you're going to be spending a long time interpreting the maps. Now, I'm not going to go through this slide because, again, the integration signs have been changed to a weird sign there. I would swear at Bill Gates, but I'm on camera, but I can't do that. And Tom is going to hold it against me if I do.
Pretty sure he's watching.
He's rapt attention. What this is showing you a time and frequency. So it's basically showing you that going from real space to Fourier space, any shape can be seen with a square can be expressed as a simply, triangle can be expressed as a sinc square, Gaussian is expressed as a Gaussian, and Morse is expressed as a single. If we take an example of the scattering from 2, 3, and 4 atoms, if we have 2 atoms, you get the scattering that looks like that plot at the top. The atoms have a regular period in this dimension. The resulting diffraction pattern is the same kind of period in that dimension. If we have 3 atoms, we get something like this. If we get 4 atoms, we get something like this. So this is real space. This is the X-ray scattering. And what you start to see in the X-ray scattering is that you get symmetry. Within the X-ray scattering, it actually reflects the symmetry of the matters. So you have an idea from the X-ray scattering what the symmetry looks like. If you look at more atoms, 8 atoms in the calculated electron scattering, and this is neutron scattering. Neutrons are also are particles, but they also have wave properties. And you can do diffraction with neutrons. The scattering actually occurs from the nucleus, not the electron cloud. And you'll notice a little thing here where with the X-rays, the intensity falls off, like markedly as you get from the center. With neutrons, it doesn't fall off as much as you get further out. If I get a chance, we'll get to that towards the end of this part, but I'm not going to explain it for the moment. If we take the 1 atom case, and we look at line across the diffraction properties and the diffraction image itself, you'll see for 1 atom, we have an arbitrary intensity of 200. If I do 2 atoms, you can see that the original intensity profile is actually the envelope of this profile here, but we've gone from the intensity of 200 to 800. So we actually have a scattered intensity. That's the square of the number of atoms in our example here. If we go to 5 atoms, we get an intensity that looks like this. This is a one-dimensional case. You'll notice that the intensity has gone up to 5,000. What's happened is that we have gone from 1 atom with 200 intensity to 2 atoms, which is 200 times 2 to the power 2 atoms squared, to 5 atoms, which is 200 times 5 squared. So the increased intensity that we get when we have a repeating unit in there is proportional to the square of the repeating units. So if you have a single molecule, no longer an atom, but a single molecule now, the intensity of a single molecule, say, is 1. Actually, 1's about, say it's 10. The intensity of a single molecule is 1. The intensity of 2 molecules, so the intensity of a single molecule is 10. The intensity of 2 molecules is 10 times 2 squared. So it's 40. There are 3 molecules of 4 molecules, the intensity becomes the square, multiplied by the square of the number of molecules. Now this is also why we want a crystal, because we would get diffraction from a single molecule. It would be a very boring diffraction picture that would look like a diffuse kind of pattern. But as soon as we start building up the number of molecules, we amplify that. We not only get custodial interference because we've now got a crystal, but we amplify the signal that we get out. So this is also why single molecule imaging is very difficult, because the signal that you get is very small compared to a crystal. You need a high intensity beam and a very, very low noise to tell. Going back to the complex number notation, here's your reflection. We give the reflection a magnitude we call f. F is the amplitude of the reflection. I is the intensity. So we have a reflection HKL, which defines the planes from a three-dimensional space. And we have the intensity is equal to A HKL squared plus B HKL squared, where A and B are the dimensions in the real axis and the imaginary axis. And it's the summation of the squares, and that gets rid of the imaginary point. So this is what the intensity of the reflection is given by. It's the summation of the real and the imaginary component. You'll notice when we do that we actually get rid of any angular information. You can't get any angular information from this. And the F squared is actually the intensity that's measured. You don't get any angular information, it's lost. Now, adding complex numbers is very easy. So if we have a reflection 1, a reflection 2, and a reflection 3, and these are added together, it's very easy that you get the real components, x1 plus x2 plus x3, the imaginary components plus y1 plus y2 plus y3, and then the intensity will be the square of these components here, but losing the imaginary information. So the actual intensity of the final intensity and phase of that final reflection will be that black line there. So we go from the first reflection to x1, y1. You take the second reflection and take it from where the first reflection ends. Take the third reflection and take it from where the second reflection ends. And that black line is the final position. And the drop down to this axis here gives you the real component, the strength of that reflection, and the angle gives you the phase of what that reflection is. So using the Argand diagram, you can add multiple reflections together and find out what the final intensity of that reflection is.
Why do you lose the imaginary?
You lose the imaginary one because this component, the B component, is actually imaginary. As soon as you start to square, well, the imaginary number is square root of minus 1. The square root of minus 1 is minus 1 times minus 1, which is 1. So you no longer have that imaginary component that's there. There's supposed to be a maths class that goes with this as well. Is that being done in this session? No. I talked to Paul about that. Jimmy was to do that one. So that's a recap of these things. Recap of that. So this may be covered in another part of the lectures as well, but I'll cover it briefly here. The atomic scattering factor is given by F equals the function over the radius of the electron density times the phase of the beam. And if you integrate over the entire space, it's the summation of the electron density in space times this imaginary component there. So that's a single scattering by a single atom. if you have the same single atoms in a unit cell, and this is a plot of the electron density across the unit cell, so these are the same atoms, these are not different atoms, your scattering is then given by the summation of the individual scattering as a function of the phase. So you can take these and do your Argand diagram with that and get that out. I just realized there's a huge error in that diagram. So because the F's, the real part, should be the same amplitude. So this should be the same length as 1, 3 should be the same length as 1 as well, because they're the same atom. So the F's will always be the same for the same atom. It's the directions that will be different depending on where the phase of the wave is. So I have to correct that diagram. I showed you that one. I showed you adding the complex numbers. Once you get this kind of situation, you'll have a real crystal which repeats. You have these electron density values. Now, unfortunately, the same mistake as in this diagram here. But essentially, within a real crystal, you start adding up all these individual components. So these should be all the same waves. So for every set of scattering, for this lattice, for this particular point here, you'll have a real quantity times the phase where the wave hits it, plus another real quantity times whatever that phase is, plus another real quantity, and your resultant reflection will look something like this. So this reflection will have this phase, and if you propagate down to where it crosses the real axis, it will have this intensity. That reflection up there, if you propagate down the real axis, it has an intensity that's about half of that. This one down here will have an intensity that is about the same as that. So what it's saying here is that even though it's the same atoms, because they're in different position in space, they'll have different phase, have the same intensity but different phase. And instead of getting data from or reflections from all of these that add up, the only time that you actually get a reflection on your diffraction pattern is when all these angles are in the same direction.
What's each one of those examples trying to show? It's showing that.
What each one of these examples is trying to show, and these arrows should be the same length. But what it's trying to show is if I look at this lattice in different directions, what I'm getting is this same intensity that's coming out, but the phase is shifted around here. And what it means is that only in the one direction where all these phases would be the same is where I'll actually get constructive interference out. So even though all these atoms are actually scattering X-rays, they're all scattering them in different phases. And if those phases don't constructively interfere, I don't get any data from that direction. And the phases will all be different because the physical X-rays actually have to travel through here as well.
Is that last line the resultant overall scatter for each unit cell is different?
Yes, the overall scattering intensity will be different depending on the phase, depending on where the phases of the individual components are.
Isn't each unit cell identical?
Each unit cell is identical, but if you have a wave that's coming in like that, the point where the wave hits here will be different from the point where the wave hits there. So the wave is not necessarily an integer unit of the size of the unit cell. So it could be, that would be really nice. But,
does that come into play in practical scattering where your incident phase is different for all your X-rays?
Well, what I'm considering here is a single X-ray wave that's coming in. If you had a coherent source, then this would make a difference. But effectively, you have an incoherent source. There's so many different waves coming in that it's the summation over a lot of it. What this is just showing you is that not every unit cell diffracts the same way. It diffracts to the same energy diffracts there, but the phase and the amplitude, the real and the imaginary component is different. And all that has to be added together.
is one unit cell scattering, the resultant scattering from one unit cell is just shifted by the phase?
Yeah.
It is just.
Yeah. Yeah. So unfortunately this diagram is wrong because these blue arrow and red arrow and the yellowish arrow here should all have the same length. That's just my bad. Why do different reflections have different intensities? Well, if you remember last time, I showed you the different planes. So there's 2, 3 lattice line, 2, 1 lattice line, 1, 0, or 2, -1. And what I've done in this is I've put the 4 atoms in the unit cell, and I've put them into these planes. And it turns out that the 2, 1 lattice line has a large electron density variation as it passes through, I call them atoms here. But these are actually, oh, sorry, yeah, they are atoms. So I have a 4-atom molecule which is in that unit cell. And you can see that the 2, 1 line passes through yellow, green, and blue. Those are 2, 1. So the 2, 1 passes through those particular atoms. In this unit cell, it passes through yellow. In the unit cell below, it will pass through green and blue. In this line here, it passes through green and blue. In the unit cell below, it passes through yellow. The 2, -1 passes through only the blue atom. And the 2, 3 lattice line passes through the red atom. So the density is related to the way the lattice, the HKL value, cuts the unit cell, and which atoms it actually cuts within the unit cell. So for example, if this 2, 3 lattice line cuts something like selenium, there would be a heavy atom in there, this would be a fairly intense reflection. There would be a lot of electron density there. Now, that's a case of a unit cell with 4 atoms. In a real unit cell, that lattice line is going to cut a lot of things. And the intensity that you actually see will be due to all those atoms that are cut. So you can say conceptually that the position of the reflection is related to the position of the atoms that you're looking at in the molecule. And the intensity is related to what those atoms are. Because you don't have a simple case where you've only got 4 atoms, but you've got hundreds of atoms in there. Each reflection has a component from all those that it passes through. So it's not as easy as that makes out. But that does tell you why the intensity varies. It's how it cuts the atoms or the electron density that it sees within that unit cell.
As a general rule, though, the higher order the indice, the lower intensity is going to be, just because you're cutting at finer and finer distances, and that would inherently have fewer atoms.
You also have the amplitude is going to be less. Yeah. Scattering by a crystal is given by this equation. It's the structure factor, or how intense the scattering is, times a function of the phases and positions in the A, B, and C directions. The total wave scattered by the crystal is a summation of all the unit cells from 0 up to unit cells in X, Y, and Z. And F is the structure factor. It's the amplitude of each reflection, but not the intensity. This is scattering by a crystal. A crystal doesn't scatter X-rays unless A times the scattering vector is equal to an integer H, B times the scattering vector is equal to an integer K, and C times the scattering vector is equal to L. These are the Lua indices. I think we'll get into scattering vectors. We do here. So I think I'm actually going to stop here, and then we'll get onto this point about scattering vectors in the next one on Friday. My voice is clear. Okay.